Broadly speaking, data can be organized either as a one-dimensional array or a two-dimensional rectangular array or a data table. So we might have raw data related to the closing price of a given stock. We might say that for stock X, the closing price on day 1 was 52, then on day 2 it was 53, day 3 it was 50, and so on. So this is a one-dimensional array where we have effectively one row of data or one column of data. This is an array. With two-dimensional data, we essentially have a table. So here, for example, we might look at different variables such as revenue per share, earnings per share, and dividends per share over multiple periods. We might have quarter 1, 2, 3, 4, and so on. And when we look at this data, notice that it is in the form of a table, because for a given quarter, we have these different variables. Then for the next quarter, we again have these variables. This is called a rectangular array or a data table. We'll now look at how to summarize data using a frequency distribution. To understand the concept of a frequency distribution, let's consider a very simple example. Say we have summary data for 200 companies, and these 200 companies are across 4 different sectors. The sectors are technology, healthcare, the financial services sector, and the industrial sector. With a frequency distribution, basically we look at how many companies fall in each sector. So for example, here we notice that 22 companies are technology companies, 50 are healthcare companies, and so on. This number 22 is the absolute frequency, because this is saying that out of our total sample size, which happens to be 200, 22 companies are in the technology sector. The relative frequency is 22 divided by the total. So 22 over 200 is 11%. This is the relative frequency. So essentially what we have here is the frequency distribution. This is also called a one-way table. This frequency distribution is based on a categorical variable. So our variable is the sector, and essentially each value here represents a category. So technology is a category, healthcare is a category, and so on. When we deal with a categorical variable, then the process of constructing a frequency distribution is very simple. We only have 3 steps. The first step is to count the number of observations for each unique value. In our example, the variable is sector, and then technology is a value, healthcare is a value, and so on. And here we have said that we identified 22 technology companies, so that's where the 22 is coming from. Then we construct a table listing each unique value and the corresponding counts. So that's what is shown over here. We show the 4 unique values. These are the 4 possible sectors and the corresponding count for each sector. Then we sort the records by number of counts in descending or ascending order. So here we've simply used ascending order. We first had technology, where we have the fewest number of companies, and then healthcare has more companies, and the industrial sector has the most number of companies. So this is a frequency distribution given a categorical variable. Now let's say we want to construct the frequency distribution for numerical data. And we will understand this process using a simple example. Say we have the summary data for the price of 100 stocks, and the price range is from 45.00 to 65.00. The first thing we do is sort the data in ascending order. Let's say our lowest number is 45.00, so that comes first, and then we sort in ascending order. The highest number, which is the 100th stock, would be 65. So this is the data that we have. Then we calculate the range of the data. This is simple. The range is 65 minus 45, which is 20. We decide on the number of bins. Let's say we want 4 bins. We then determine the bin width. The bin width is equal to the range divided by the number of bins. 20 over 4 is 5. We then define the bins, and this is also fairly straightforward. We are starting with 45, so the first bin will be 45 plus 5, which is 50. So the first bin is from 45 to 50. Then the next bin will be 50 plus 5. So that is going to be from 50 to 55 and so on. So this is the second bin. We come up with our 4 bins as shown here. This is the first bin, second bin, third bin, and fourth bin, going all the way up to 65. Then we determine the number of observations in each bin. So we have this data. We look at all the numbers that go from 45 to just under 50. Those will go in the first bin. So in our example, we have 25 observations that are in the first bin. Now a question is, what would we do with a stock that is at 50? And the answer is this stock will go in bin 2. And the way you remember this is, if this stock is given a choice as to whether it wants to go with the big boys over here or the small boys, this is going to pick the big boys. So whenever something is on the border, it will go in the bigger bin, and that's what is happening. Now, once we put all the stocks in the respective bins, that's what gives us all these absolute frequency numbers. And essentially, what we then do is construct a table of the bins listed from smallest to largest. So we have the smallest bin, then larger, and then the largest, and the number of stocks that are in each bin. Cumulative frequency simply takes all the numbers till that point. So if we have 50 to 55, this 60 means that we have 25 plus 35 is equal to 60 stocks that are up till 55, and so on. This number over here, 100, will be the total number of stocks. The relative frequency is a number in decimal or percentage terms. So for the first bin, we have 25 out of 100, that is 0.25 or 25%. Second bin, we have 35 out of 100, so that's 0.35 or 35%. And the same logic is true for bins 3 and 4. Cumulative relative frequency is the sum of everything till that point. So 0.6 is equal to 0.25 plus 0.3. 0.89 is equal to 0.25 plus 0.35 plus 0.29. And then obviously, when we get to the final number, which is 65, then the cumulative relative frequency is 1, or we can say this is 100%. One final note of caution: if we have a stock that is at 65, then obviously with this stock, we don't really have an option to put this in another bin. So a stock that's at 65 will go into this final bin. Now let's look at some practice questions. On the exam, it's unlikely that you will be asked to construct a frequency table, but you need to know the process and you need to know the terminology. This question is about terminology. The actual number of observations in a given interval is called what? The answer here is absolute frequency. And the answer over here also explains the other terms that we've talked about. Which of the following is most likely to be accurate? An observation can fall in more than one interval. So this question is more about the process. And we know that with a frequency table, a given observation can only fall in one interval. Therefore, the first option is not right. The data is sorted in descending order for the construction of a frequency distribution. This is not true because data is actually sorted in ascending order. The cumulative frequency tells the observer the fraction of the observations that are less than the upper limit of each interval. This is a true statement. Therefore, C is the best answer. Moving on to summarizing data using a contingency table. A contingency table is a tabular format that displays the frequency distributions of two or more categorical variables simultaneously. Let's take a simple example. Say we have 500 stocks and we are evaluating these 500 stocks along two variables. One variable is the market capitalization variable. The other is the sector variable. Under market capitalization, we take three possible categories. So under market capitalization, we can either have small cap, mid cap, or large cap. And under sector, we can have the financial sector, fast moving consumer goods or FMCG, information technology, and real estate. So notice here we have two different variables, and then we will look at the distribution based on these two variables. This number 44 is a joint frequency because 44 represents the number of stocks that are both small cap and that belong to the financial sector. 54 refers to the number of companies that are mid cap and part of FMCG. So all these numbers that are in the middle represent a joint frequency. The next important term is marginal frequency. 261 is a marginal frequency. This represents the number of small cap stocks. Similarly, 142 is a marginal frequency and 97 is a marginal frequency. The numbers over here also are marginal frequencies. 102 represents the total number of stocks in the financial sector. 230 represents the total number of stocks in the FMCG sector, and so on. So key point is that joint frequencies are in the middle, marginal frequencies are here at the edges. Now let's talk about two important applications of a contingency table. The first application that we need to know is that a contingency table can be used to evaluate the performance of a classification model. So what is a classification model? Let's understand this through a simple example. Say we have a model for classifying companies into two groups or two categories, those that default on their bond payments and those that do not default. Say we are evaluating 1,000 companies. So we have company 1, 2, all the way down to 1,000. And obviously there are characteristics associated with these companies such as the debt ratio and so on. We pass each of these companies through a model. This is called the classification model. And the model evaluates each company and then identifies companies that are likely to default and companies that are not likely to default. So this classification model is basically giving a prediction. And that is shown over here. So there is this concept of a predicted default. The model predicts that 160 companies are likely to default and 840 companies are not likely to default. Now, in this table, obviously one variable is the predicted default or the prediction that there is no default. The other variable is the actual data. So we also look at these 1,000 companies and whether they actually defaulted or not. So this is a contingency table in the sense that it has two variables, the variable related to predicted default and the variable related to actual default. In both cases, the variables can take on two possible values. Yes, that the default is predicted, and no, that default is not predicted. And with the actual default, the two values are yes, the company did default, and no, the company did not default. These values at the edges are marginal probabilities. So 160 means that the model is predicting that 160 will default and 840 will not default. These numbers in the middle are joint probabilities. So this 150 means that there are 150 companies where the model predicted a default and there was indeed a default. 10 means that the model predicted a default, but in reality, these bonds did not default. So this is an error. With this row, what we have is the model predicting no default, but in actuality over here, we did have 6 defaults. So we have 6 situations where the model said that a default will not happen, but in reality, the default did happen. So this is also an error. So this sort of a table where we are evaluating a classification model is called a confusion matrix. So remember the fact that the confusion matrix is a particular type of contingency table, and this confusion matrix is allowing us to evaluate how good the classification model is. Now we can say that this model is fairly good because out of 160 predictions where the model said that yes, there is going to be a default, there were only 10 mistakes. And in a situation where the model said that there will be no defaults, out of 840 predictions of no default, there were only 6 mistakes. So overall, this model appears to be reasonably good based on a study of the confusion matrix. Another application is to investigate potential association between two categorical variables. One way to test this potential association between categorical variables is to follow a 3-step process. Step 1 is to add marginal frequencies and the overall total to the contingency table. So we will discuss this through an example on the next slide. The next part is to use marginal frequencies to construct a table with expected values of the observations. And step 3 involves the usage of a chi-squared statistic. So let's understand this through an example. Say we have 200 mutual funds, and these mutual funds are classified along 2 parameters. The first is fund style. So here we have either growth or value, and the other is the risk level, where we have either low risk or high risk. So this is the data. These are the joint probabilities that are given. We don't have the marginal probabilities at this stage, and the total number though is given. The total number is 200. So how can we use a contingency table to test for independence between fund style and risk level? Step 1 is to add marginal frequencies and the overall total to the contingency table. So if we go with the observed values over here, the numbers in the middle are based on what is given. Then we come up with the marginal frequencies. So 165 here means that we have 165 low risk funds, and 35 means that we have 35 high risk funds. This 86 means that we have a total of 86 growth funds, and we have 114 value funds. So 200 is the total number of funds. The same numbers can be expressed in percentage terms over here. The second step is to use marginal frequencies to construct a table with expected values of the observations. And here I'll show you how to come up with these expected values. Let's say we want this expected value, which corresponds to growth and low risk. To come up with the expected values, we need to multiply the two marginal values. So we take the marginal value for growth, which is 86, and we multiply this with the marginal value for low risk, that is 165, and then we divide by the total number, which is 200. This will give us 70.85. Similarly, to come up with 19.95, we will multiply this marginal value of 114 with 35 and then divide by 200. Just to make sure you understand this, make sure that you can come up with these two values. Then step 3 is to use the actual values and the expected values to derive what is called the chi-square test statistic. This statistic is then compared to a value from the chi-square distribution table for a given level of significance. If the test statistic is greater than the chi-square distribution value, then we can conclude that there is a significant association between the categorical variables. So most probably, if you haven't already studied hypothesis testing, this will not make a lot of sense. So for now, just take it as a given that we decide whether or not there is an association based on expected values and based on the actual values. Just read this a few times and then come back to this after you've done the reading on hypothesis testing.